Walk into a dense forest, stand completely still, and listen. If you don't hear anything, it is easy to assume the woods are empty. But that silence is an illusion created by the biological limits of human ears, which are entirely deaf to the high-frequency, ultrasonic world buzzing right in front of us. Because we could only perceive a narrow slice of the acoustic spectrum, science operated under a strict assumption for decades. If an animal made a noise, researchers concluded it was either a hardwired alarm grunt or a simple imitation. We established strict benchmarks to separate true language from mere animal noise. To cross the threshold, a species had to use arbitrary names to identify each other and employ syntax, the ability to string distinct sounds together to build complex grammatical sentences. Now, researchers are deploying high-fidelity digital bioacoustics, super-powered hardware dropping into oceans and forests to record 24 hours a day. They are taking those massive audio files and feeding them directly into the same artificial intelligence models that power human translation software. By pairing highly sensitive sensors with pattern-recognizing algorithms, we are finally taking off our biological blindfolds. The data reveals that the natural world is already deep in conversation. Look at this family of elephants moving across the African savanna. For a long time, we thought their deep, vibrating rumbles were just general broadcasts. Isolating these frequencies, researchers located the first foundational block of language, the concept of arbitrary names. When running thousands of these low-frequency calls through machine learning tools, scientists noticed a deliberate pattern. An elephant produces a specific rumble when addressing one particular member. When played back through a hidden speaker, only the targeted elephant reacted. Certain dolphins and birds use signature sounds to identify themselves by mimicking the other animal's call. The elephants use a distinct abstract signal that stands in for an individual identity without copying the sound of the receiver. Moving from the savanna to the dense forests of the Ivory Coast, we find wild chimpanzees clearing the next major linguistic hurdle, syntax. This is the ability to take separate sounds and combine them to create entirely different meanings. This diagram shows how they construct phrases. Left is the waveform for a who, a resting sound. Next is a pant, a playing sound. When the two sounds merge, the meaning shifts. The chimp is now signaling, I am building a nest. By assigning labels to relatives and structuring sounds into new phrases, these animals wield abstract concepts to navigate their tight-knit social hierarchies. Drop thousands of feet below the surface, and translation becomes harder. Here, we share zero biological context or sensory environment with the speaker. Sperm whales communicate by firing off tight, rapid bursts of percussive clicks, known as codas. To the human ear, it sounds closer to mechanical ticking than a biological voice. This creates what researchers call a semantic gap. Because a sperm whale experiences a reality defined by crushing pressure and echolocation, we lack shared reference points to map human words onto their clicks. To bridge that gap, Project STEADY turned to an AI model built to analyze human music. They modified this system, calling it WHAM, and fed it databases of recorded sperm whale codas. This data visualization illustrates what the algorithm found. The AI detected hidden structural rules, mapping out subtle variations in rhythm and ornamental beats. The model is now so accurate, it predicts the exact sequence of upcoming clicks before they happen. We may not understand the subjects they are discussing, but the math confirms it. A highly organized language echoes through the deep ocean. Decoding these structures brings us to an uneasy threshold. With models like Nature LM and Dolphin Gemma, algorithms are no longer just transcribing audio. They are now capable of generating synthetic, localized animal speech on command. Researchers have already used these generated calls to direct the movement of honeybees and exchange signals with dolphins, automating the first two-way interactions between human technology and wild animal social systems. But speaking a language you don't fully understand carries immense risk. Broadcasting synthetic calls back into the wild through playback experiments can trigger severe distress, confusion, and panic among unsuspecting animal populations. We are already interfering with their conversations in a much blunter way. From the roar of shipping engines to the blast of seismic air guns, human-made noise pollution is saturating these delicate environments. This acoustic smog acts like a signal jammer. It cuts off communication networks, stunts the growth of embryos, and blinds marine species that rely on sound to navigate, doing massive damage before we ever learn how to talk to them. Our historical definition of language, once reserved strictly for humans, has collapsed under the weight of this new acoustic data. These algorithmic maps document a sophisticated internal reality that existed long before our arrival. We now have the mathematical proof required to recognize these species as speaking, thinking beings, and the data to show how easily we can silence them.